Today I'm gonna introduce about dextrin DADMAC MBA hydrogel electrolyte for sodium-ion batteries. Recently, sodium-ion batteries have been rapidly developed for large-scale energy storage systems. Because of the abundance and low cost of sodium resources, it has become the most promising alternative to lithium-ion batteries. The electrolyte lowers quite a large part of energy storage systems, such as cycling, realistically possible performance, rate capability, and safety. I use gel polymer electrolytes in this project, and the advantages for using it as electrolytes are suppression of dendrite growth, reduce reactivity with liquid electrolytes, improve safety. Better shape flexibility is it. Dextrin DDMC MBA gel electrolytes main properties are flexible, non-toxic, high ionic conductivity, good mechanical properties, and wide potential window than glass fiber. Diammonium chloride is widely used in water treatment and biology because it is non-toxic, hydrophilic properties, and antibacterial activities. DDM gel electrolyte has double network structure. The hard and soft components of a double network make DDM gel flexible and tough. This chemical structure has the advantage to overcome the drawbacks. The first network polymer was synthesized by a free radical polymerization technique using KPS as an initiator. MBAA lowers as cross-anchor in this reaction, and DADMAC is monomer in this reaction. DADMAC monomer is in aqueous solution, and it is cross-linking with MBAA. Second network is dextrin polymer, and its polymer chain has high molecular weight. One of the characteristics of DDN hydrogel is that 0- anion of polymer has ion exchange reaction between salts or anions like ClO4- or BF4-. I would like to explain the characteristics of DDM gel when sold to aqueous electrolyte in this page. When the DDM gel was soaked in DI water, the area increased more than 16 times, but mechanical properties are significantly decreased. When the DDM gel soaked in NaClO4 or NaBF4, the area of gel is shrinked a little, but mechanical properties are significantly improved. Black lines data is DDM hydrogel before swelling. Red line data is DDM hydrogel swelled in NaClO4 solution, and orange line is swelled in NaBF4 solution. As shown in the stress strain curves, after swelled in ClO4 or BF4 solution, the gel's strength and toughness are increased. This graph is TJ graph. Black line data is DDM ClO4 hydrogel, and red line data is DDM hydrogel. The first weight loss before 100 degrees was due to the water evaporates from the hydrogel. After water evaporates, the degradation mechanism of the DDM hydrogel is divided into two stages. In the first stage of the hydrogel degradation, a methyl group of DDMAC is decomposed and it binds with Cl- anion to produce CH3Cl. Similar with above, in hydrogel with NaCl4 degradation, CL4 anion bind with the methyl group of the ADMAC. The last degradation took place at 410 Celsius to 460 Celsius, and DDM and DDM04 polymer were degraded 20%. It was confirmed that the decomposition temperature changed according to the salt's anion. These images are same image showing pore structure and uniformly interconnected 3D structure of DDM gel, hydrogel electrolytes. DDM hydrogel is very hydrophilic, and this gel shows up easily in water. The synthesis of DDM gel was confirmed by solid-state CNMR and FTIR spectra. The FTIR spectrum of DDM hydrogel has sharp peak at 1647 and 1476 and 1080. 1476 peak is C double bond peak, and 16747 peak is CN group bending vibration of ring from the DADMSC. When the DADMSC monomer reacts, C double bond is released, and it can be seen by 1476 peak decreased. In graph B and C, all samples containing CL4 anion shows a large sharp peak at 1080. This page shows the CNMR spectrum of DDM hydrogel, and main peaks appears before 50 ppm. Black line data is DDM hydrogel, and the red line data is DDM CL4 hydrogel. The main peaks of DDM and DDM CL4 were almost same, and there was a slight change in the peak of the CL4 anion bonding part. This graph shows that the chain structure of DDM has remained almost unchanged. This is EDS data for hydrogel. The top is a DDM polymer washed in DI water, and the bottom is the DDM CL4 polymer washed in DI water. Sodium atoms were evenly distributed in polymer washed with NaCl4 solution. Look at the picture of polymer before and after swelling. The polymer color is changed after washing, and the reason is that the NaCl4 source is trapped in the hydrogel. This gel is tested in water insert solution, and 15 more concentration of NaCl4 is NaCl4. A graph is EIS data for explaining just ionic conductivity. In this graph, red line is gel study in CL4 solution, and black line is the gel study in BF4 solution. CL4 study in sweat gel has high ionic conductivity, and it has 22 millisiemens per centimeter. It shows significantly higher ionic conductivity than other polymer gels. B graph is LSV graph for check the open window voltage. The temperature is stable until 2.5 volt. It was stable because gels and water insert system prevents the evaporation of water. This page is DDM hydrogen fuel cell data. Cathode is MVP and anode is activated carbon. Electrolyte is DDM hydrogen electrolyte sold in water in salt solution, 15 more concentration NaCl4. A graph is hybrid batteries 4 cell with graph. B is GCD profile obtained at different current density, and C is plot of specific capacity versus current density. MVP's theoretical capacity is 118 milliampere hour per gram, and 4 cells specific capacity is almost 80 milliampere hour per gram at first cycle. In graph C, DDM hydrogen battery has a good rate performance until 5 ampere per gram. Graph D is cycle and charge discharge capacity data. As shown in graph D, cycle stability is not stable due to the problem of vanadium dissolving in MVP. The suitable cathode for sodium-ion battery aqueous system is not exist yet, and it is the biggest obstacle to aqueous sodium cells. I am planning to increase cycle stability in various ways. Thank you for listening. Thank you.